Hello everyone, very good evening to all of you. Good evening everyone, good evening, good evening. Okay, so shall we start today's session? Audio and video is fine. Audio, video both are fine. Shall we start today's session? Okay. So let's start today's session. Right, so far we discussed about the fluid properties, right? Density, specific gravity, weight density, viscosity, bulk modulus, compressibility, viscosity, surface tension, capillarity, wettability property, non-wettability property, right? So far we discussed number of properties related to the fluid. Now let's discuss about the types of fluid. So far we didn't discuss about the types of fluid. So let's start our discussion with types of fluid. So if I'm talking about the types of fluid, basic classification, right? The basic classification of the fluid is, right, there are two types of fluid. One is the ideal fluid and second one is the real fluid, right? Basic classification of the fluid. Basic classification basic classification of fluids. Basic classification of fluids. So if you classify fluids in very basic manner, then there are two types of fluids. One is a ideal fluid. One is a ideal fluid. And second one is a real fluid, right? Second one is a real fluid. So can anyone tell me what is the ideal fluid? So can anyone tell me what is the ideal fluid? Can anyone tell me what is the ideal fluid? What is the ideal fluid? What is the ideal fluid? What is the basic definition of the ideal fluid? Right, so a fluid, we can define ideal fluid in a manner, a fluid which have zero viscosity, right? A fluid which have zero viscosity, a fluid which have zero viscosity, or you can say inviscid also, right? Inviscid. And why ideal fluid is inviscid or zero viscosity? Because in case of the ideal fluid, right, there is no intermolecular attraction force between the molecules, right? So whenever I say ideal fluid, so in case of the ideal fluid, there is no cohesive force. In case of the ideal fluid, no cohesive force. And since there is no cohesive force, therefore there is no viscosity on the fluid. So ideal fluid is a fluid which have zero viscosity, or you can say inviscid. Second, zero surface tension. We already discussed about the surface tension, right? Surface tension is a interface property, and surface tension is because of the imbalance between the cohesive force and the adhesive force. As I already told you, in case of the ideal fluid, there is no cohesive force, so obviously there is no surface tension, or we can say there is a zero surface tension. So ideal fluid have zero surface tension. And third very important point, ideal fluid is treated as incompressible. Ideal fluid is treated as incompressible. And we know that what is the meaning of the incompressible? Change in volume is zero. right? Or you can say volume is constant, change in volume is 0, change in density is 0, change in density is 0, or you can say density is constant, right? Bulk modulus is infinite, bulk modulus is infinite, or you can say that compressibility is 0, right? So if I say fluid is incompressible, so either you can say change in volume is 0, or you can say density is constant, or you can say bulk modulus is infinite, or you can say that compressibility is 0. So if anyone asks you what is the ideal fluid, so you can define ideal fluid, a fluid which have zero viscosity, zero surface tension, and incompressible. Such type of fluid is known as the ideal fluid, right? So this is the definition of the ideal fluid, right? Now what is a real fluid? So obviously a fluid which is not ideal, and realistic fluids are obviously real, right? That practical fluids are real. Ideal fluid is a hypothetical concept. Ideal fluid is a hypothetical concept. Ideal fluid concept come into picture to make the problems easy, right? That's why ideal fluid concept come into picture. But we know that nothing is ideal, we know that, right? So practical fluids are the real fluids, practical fluids are the real fluids, right? So real fluid we can define a fluid which is not ideal. Simple. A fluid which is not ideal. A fluid which is not ideal. Right. Now again we can categorize real fluid in two ways, right? Real fluids are further categorized in two ways. First as a Newtonian fluid, and second as a non-Newtonian fluid, right? This ideal fluid is further classified as Newtonian fluid, Newtonian fluid, Newtonian fluid, and non-Newtonian fluid. Newtonian fluid and non-Newtonian fluid. Non-Newtonian fluid. Non-Newtonian fluid. We already discussed about the Newtonian fluid, right? We already discussed about the Newtonian fluid. So what is a Newtonian fluid? A fluid which follows the Newton's law of viscosity is called the Newtonian fluid. As simple as, we already discussed about this in a Newton's law of viscosity concept, right? Newtonian fluid is a fluid which follows the Newton's law of viscosity, that is called the Newtonian fluid, right? And non-Newtonian fluid, obviously a fluid which does not follow the Newton's law of viscosity, that is called the non-Newtonian fluid. As simple as. Fine. Now beta, come to the very, very important concept, right? The most of the time in interview this question is asked, there is any difference between the ideal fluid and the ideal flow? Ideal fluid versus ideal flow. Ideal fluid versus ideal flow. Can anyone tell me what is the difference between the ideal fluid and the ideal flow? Right? The flow of ideal fluid is the ideal flow, or there might be chances the real fluid flow is also ideal flow. Please try to understand my question. What is the difference between the ideal fluid and the ideal flow? So if I say ideal flow, so ideal flow means the flow of ideal fluid, that is a mandatory, the flow of ideal fluid is the ideal flow, or there might be chances the flow of real fluid is also ideal flow, right? So beta, we can say, see, please try to understand this now. Please try to understand the flow of ideal fluid, flow of ideal fluid is ideal flow. Flow of ideal fluid is ideal flow, but ideal flow, but in ideal flow But in ideal flow, ideal fluid is not mandatory. Ideal fluid is not mandatory. Ideal fluid is not mandatory. That fluid may be that fluid may be real fluid. That fluid may be real fluid. That fluid may be real fluid. Is it clear to everyone? Is it clear to everyone? Please try to understand. This is a very beautiful concept, right? The flow of ideal fluid is ideal flow. That's fine, right? If fluid is ideal and flow of that fluid occurs, then definitely that is an ideal flow. But in ideal flow, ideal fluid is not mandatory. That fluid may be real fluid. So beta, actually, right, let us consider a plate. Let us consider a plate, right? Let us consider a plate, and above the plate, that fluid is flowing, right? And obviously this is a real fluid. This is a real fluid. So if this is a real fluid, so definitely this fluid have some viscosity. This fluid have some viscosity. And let us consider that free stream velocity of this fluid is u infinite, right? So what is the free stream velocity, right? The velocity of the fluid before come into contact with the plate, that is called the free stream velocity, right? So u infinitive is free stream velocity, right? So beta, when real fluid come into contact with the surface, when real fluid come into contact with the plate surface, then there is a formation of the boundary layer. Then there is a formation of boundary layer like this, right? Then there is a formation of the boundary layer like this. This is the boundary layer. This is the boundary layer. This is the boundary layer. So actually what happened in the boundary layer? In the boundary layer, so let us consider this is the region number 1 and this is the region number 2, right? This is the region number 1, this is the region number 2. So actually what happened, whenever the real fluid passes over the plate, over the surface, over the real surface, then your fluid flow is separated into two parts, right? Your fluid flow is separated, or I can say your fluid field is separated into two parts like this, right? Inside region, outside region, and this is the boundary layer. The region number 1, this region is called viscid region. This region is called viscid region, and this region is called inviscid region. Inviscid region. So actually what happened in the viscid region? What happened in the viscid region? So beta, actually in the viscid region, if you see layer to layer velocity, right? If you see the layer to layer velocity, so layer to layer velocity is not same, right? We know that if this is your coordinate system, this is the x direction and this is the y direction, we know that at y is equal to 0, right? At y is equal to 0, what is the velocity of the fluid layer? That fluid layer velocity is same as the plate velocity. And if we assume this plate is stationary, that means a fluid layer which is at y is equal to 0 is also stationary. So this layer which is very very close to the plate having 0 velocity, right? And as we are moving perpendicular to the plate, then velocity of the layer increases. So let us consider here at this particular, right, at this particular layer, the velocity is approximately equal to the free stream velocity. So this velocity is approximately equal to the free stream velocity. Here the velocity is 0. So beta, definitely that velocity, each layer having different velocity like this. So inside the boundary layer, or in a region number 1, each layer having a different velocity, right? And since each layer having different velocity, so definitely the friction come into picture. That's why inside the boundary layer we can say the flow is frictional flow, right? The flow is frictional flow. Whereas if I'm talking about the outside the boundary layer, that means in a region number 2, in a region number 2, region number 2. So beta, what happened in region number 2? In region number 2, that viscous effect of the fluid is negligible, right? Inside the boundary layer, that viscous effect or viscous force is highly significant, whereas outside the boundary layer, that viscous force is negligible. And viscous force is negligible, that's why each layer outside the boundary layer, each layer having same velocity, and that is equal to free stream velocity. See, velocity profile outside the boundary layer, right? Outside the boundary layer, each layer having same velocity, right? This velocity is u infinity. So if I ask you, outside the boundary layer, the friction force come into picture or not? Outside the boundary layer, that friction force come into picture or not? Like, see, inside the boundary layer, definitely the friction force come into picture. Why friction force come into picture? Because the relative velocity between the layers exists because of the viscosity, because of the viscous effect. Whereas outside the boundary layer, that viscous effect is negligible, and since viscous effect is negligible, therefore each layer having the same velocity. And since each layer having the same velocity, that outside the boundary layer there is no friction. If there is no friction, that means that fluid flow we considered as an ideal flow, right? In case of the ideal flow, there is no friction. In case of the real fluid, in case of the real flow, right? In case of the real flow, definitely friction come into picture. But if I say ideal flow, in case of the ideal flow, there is no viscous force, there is no friction force. So outside the boundary layer, in this region, we consider flow as an ideal flow, right? So though fluid is a real fluid, but outside the boundary layer, we consider flow as an ideal flow. I hope you can understand this, right? So this difference is clear or not? It is not mandatory, beta. The flow of ideal fluid is the ideal flow. The flow of real fluid may be ideal flow. Is it clear or not? Tell me, is it clear or not? So outside the boundary layer, the flow is ideal flow, right? Outside the boundary layer, the flow is ideal flow. Fine. Now come to this classification, right? Come to the real fluid classification of the real fluid. So I already told you the real fluids are classified as Newtonian fluid, the real fluids are classified as Newtonian fluid and non-Newtonian fluid. Newtonian fluid and non-Newtonian fluid, right? And science which deals with the non-Newtonian fluid is called rheology, right? Science which deals with non-Newtonian fluid, is called rheology. Right? The science which deals with the non-Newtonian fluid is called rheology. Now come to the non-Newtonian fluid. So beta, non-Newtonian fluid are again two types. Non-Newtonian fluid are again two types. Right? Non-Newtonian fluid are again two types. One is a time dependent non-Newtonian fluid and second one is a time independent time independent, time independent, time independent non-Newtonian fluid, right? Time independent non-Newtonian fluid, time independent non-Newtonian fluid. And second one is time dependent dependent time dependent non-Newtonian fluid, time independent non-Newtonian fluid and time dependent non-Newtonian fluid. Now time independent non-Newtonian fluid is again categorized as three types, right? This time independent non-Newtonian fluid is further classified in three ways, that time independent non-Newtonian fluid. So time independent non-Newtonian fluid is further classified in three ways. That first one is a dilatant fluid. Right. The second one is a pseudoplastic fluid. Pseudoplastic fluid, right? And third one is a Bingham plastic fluid. Bingham plastic fluid, right? So time independent non-Newtonian fluid is classified in three ways: dilatant, pseudoplastic and the Bingham plastic. Now come to the time dependent non-Newtonian fluid. So time dependent non-Newtonian fluid is further classified in two ways. That is a rheopactic and the thixotropic. Rheopactic fluid and thixotropic fluid. Thixotropic fluid, right? So please try to understand. Real fluids are classified. See, this is a basic classification. This is the very basic classification of the fluids: ideal fluid, real fluid. What is ideal fluid? A fluid having zero viscosity, zero surface tension and incompressible. That fluid is an ideal fluid. And a fluid which is not ideal, that is a real fluid. So real fluid is further classified as a Newtonian fluid and non-Newtonian fluid, right? Now Newtonian fluid, we already discussed about the Newtonian fluid in Newton's law of viscosity, right? So what is a Newtonian fluid? It is very simple: a fluid which follows the Newton's law of viscosity. Newton's law of viscosity is called Newtonian fluid. Can anyone tell me examples? Can anyone tell me what are the examples? Can anyone tell me? I discussed number of examples. Can anyone tell me what are the examples? Can anyone tell me what are the examples? Right. Air, water, kerosene, right? Air, water, kerosene, petrol, benzene, glycerine, right, etc. These are the example of the Newtonian fluid, right? And if I ask you what is the relation between the shear stress and the shear strain rate, in case of Newtonian fluid, what is the relation between shear stress and the shear strain rate? In case of the Newtonian fluid, what is the relation between shear stress and the shear strain rate? So what is the relation? That tau is equal to that is mu du by dy. This is the relation between shear stress and the shear strain rate in case of the Newtonian fluid. Right. Now, if I am talking about the non-Newtonian fluids, so science which deals with the non-Newtonian fluid, that is called the rheology. And non-Newtonian fluids are two types. One is a time-independent non-Newtonian fluid, and second one is a time-dependent non-Newtonian fluids. So what are the time-independent non-Newtonian fluids? Dilatant fluid, pseudoplastic fluid, Bingham plastic fluid. These are the example of time-independent non-Newtonian fluid. And if I'm talking about the time-dependent non-Newtonian fluid, so rheopactic and the thixotropic, these are the time-dependent non-Newtonian fluid. Fine. Now, so we know the, right, we know the shear stress versus shear strain rate, shear stress versus shear strain rate relation for the non-Newton, for the Newtonian fluid. We know that, right? In a similar fashion, there must be relation between shear stress and the shear strain rate for the non-Newtonian fluid also, right? There must be relation between shear stress and the shear strain rate, right? There must be relation between the shear stress and the shear strain rate for the non-Newtonian fluid also, right? So what is the shear stress versus shear strain rate relation for the non-Newtonian fluid? So that is given by the, right, there are a number of models related to the relation between the shear stress and the shear strain rate for the non-Newtonian fluids. And one famous model is the Ostwald-Dewey model. Ostwald-Dewey model. Right, Ostwald, check spelling na, Ostwald, that Ostwald, right, Ostwald-Dewey model, right? And according to the Ostwald-Dewey model, what is the relation between the shear stress and the shear strain rate for the non-Newtonian fluid? So tau is equal to tau naught plus a into du by dy to the power n, right? This is a very popular model for the non-Newtonian fluid, that Ostwald-Dewey model. And as per the Ostwald-Dewey model, this is a relation between the shear stress and the shear strain rate for the non-Newtonian fluid, where that tau naught, tau is a shear stress, obviously that tau is a shear stress, du by dy is the shear strain rate, or you can say velocity gradient in y direction, velocity gradient in y direction, right? What is the tau naught? The tau naught is the yield shear stress. The tau naught is the yield shear stress. Yield shear stress means this is the minimum shear stress which is required to establish the flow, right? Yield shear stress means this is the minimum shear stress which is required to establish the flow, right? That is a tau naught, right? Now come to the A. Right? That A is flow consistency index, right? Or you can say this is the fluid consistency index, or you can say flow consistency index, right? That is a A. Whereas N is the flow behavior index, right? N is the flow behavior index. That N is the flow behavior index. So in a Wallah model, this tau is the shear stress experienced by the fluid layer. This du by dy is the shear strain rate or velocity gradient in a y direction. The tau naught is the yield shear stress. This is the minimum shear stress which is required to establish the flow. Right? A is the flow consistency index, and N is the flow behavior index. And in this mathematical expression, or in this particular expression, that tau naught, A and N are a constant. For a particular fluid, tau, A and N are constant for a particular fluid. Is it clear? Till this point it is clear or not? But till this point it is clear or not? Okay. Now, if I'm talking about the Newtonian fluid, so can anyone tell me what is the value of tau naught, A and N for the Newtonian fluid? For Newtonian fluid, if you use this model, if you use this Wallah model, so for Newtonian fluid, can anyone tell me what is the value of A, what is the value of tau naught, and what is the value of N? So beta, obviously for the Newtonian fluid, that tau naught is equal to 0. For the Newtonian fluid, what is the Newton's law of viscosity? That tau is equal to, this is mu du by dy. Correct, na? Tau is equal to mu du by dy. Right? So for the Newtonian fluid, the tau naught is 0. That N value is equal to 1. And A is equal to, that is mu. This is for Newtonian fluid. Is it fine? Okay. Now, this is the, let us consider, this is the equation number 1. This Wallah model, this equation I am considering as equation number 1. So from equation 1, or in equation 1, if we assume that tau naught is equal to 0, please try to understand this. In equation 1, if we assume that tau naught is equal to 0, so we can write in this way, na, that tau is equal to A du by dy to the power n. We can write in this way. Right? Now, you can write in this way also. This is tau is equal to A into, this is du by dy to the power n minus 1 into du by dy. We can write in this way also now. Right? We can write this mathematical expression in this way also, that tau is equal to A du by dy to the power n minus 1 du by dy. And let us consider this term as eta. Let us consider this term as eta. Right? So we can write this is equal to eta into du by dy. Right? We can write in this way. This term is treated as a eta. This is the eta. That eta is equal to A into du by dy to the power n minus 1. So this term is replaced by eta. So we can write in this way, eta into du by dy. Now beta, if you see this expression, let us consider this is the equation number 1 like this. Or let us consider this is the equation number A. This is the equation number A, and this is the equation number B. So if you see the equation A and equation B, right, and if you relate equation A and equation B, right, then you can understand this mu is nothing but the viscosity, right? This mu is nothing but the viscosity. In the Newton's law of viscosity, this mu is the viscosity. So if you relate this equation and this equation number A and equation number B, so beta, can we say this eta also kind of viscosity? we can say na this eta is also kind of viscosity, right? And this eta is called apparent viscosity. This eta is called, that eta is called apparent viscosity. This eta is called apparent viscosity, right? Please try to understand this, right? This eta is called apparent viscosity. And we know that this, right, this viscosity, if we already discussed about the non-Newtonian fluid, we already discussed about the Newtonian fluid. And in Newtonian fluid, if you draw shear stress versus shear strain rate plot, if you draw shear stress versus shear strain rate plot, then beta, for the Newtonian fluid, this is the straight line. For the Newtonian fluid, this is a straight line, and this slope represent the, right, this slope, let us consider the slope is tan theta. This slope represent the viscosity. So in a similar fashion, for the non-Newtonian fluids, right, in a similar fashion, for the non-Newtonian fluids, this apparent viscosity is also the slope of tau versus, or shear stress versus shear strain rate plot, right? This apparent viscosity also represents slope of tau versus shear stress versus shear strain rate, slope of tau versus du by dy plot in case of non-Newtonian fluid, in case of the non-Newtonian fluid. So if you draw the shear stress versus shear strain rate plot for the non-Newtonian fluid, so that slope represent the apparent viscosity. Is it clear or not? Is it clear or not? Is it clear to everyone? Is it clear to everyone? Tell me fast. Is it clear? Is it clear? Fine. Now see here. When that eta is equal to, this is A into du by dy to the power n minus 1. Correct, na? Right, that eta is equal to A du by dy to the power n minus 1. Right? Now, see here, and this is nothing but the apparent viscosity. I already discussed beta, this is nothing but the apparent viscosity. This is the apparent viscosity. Apparent viscosity. This is nothing but the slope of shear stress versus shear strain rate plot for the non-Newtonian fluid. Simple. Right? Now see, if you see this mathematical expression, then there are three values of n are possible. That one value is n is equal to 1. The second value is n is greater than 1. And third one is n is less than 1. N is less than 1. If I'm talking about this n, that A in n is nothing but the flow behavior index. So if I'm talking about the flow behavior index or nothing but the n, so beta n may be equal to 1, that n may be greater than 1, that n may be less than 1. So we know that if n is equal to 1, that means that fluid is nothing but the Newtonian fluid. Right? If your n is equal to 1, then your viscosity is not function of du by dy. Viscosity is not function of du by dy. If you change du by dy, viscosity not changes. Are you getting my point? And n is equal to 1. So that eta is equal to A, right? Eta is equal to A, or simply you can say that eta is equal to mu. Your eta or mu is not changing with respect to du by dy. It is not changing with respect to du by dy, right? Du by d eta, or I can say Newtonian fluid mu is not function of du by dy, right? And also we know that this is the graph tau versus du by dy, right? This is the graph, na? This is the graph. This is your slope. This is the slope. This is the slope, and this slope is nothing but the mu. So if you increase du by dy, that dynamic viscosity does not change. So when n is equal to 1, that means that is for the Newtonian fluid. Your viscosity is not function of du by dy. When you change du by dy, viscosity not changes. Simple. Now come to the n is greater than 1. So what happened when n is greater than 1? So beta, if n is greater than 1 and you increase du by dy, then what about this apparent viscosity? Tell me. Right? If n is greater than 1, and you increase the du by dy, then what happened with the apparent viscosity? Tell me. What happened with the apparent viscosity? So it is very simple. If n is greater than 1, that means n is greater than 1, so this is positive. And when you increase du by dy, your apparent viscosity increases. Is it fine now? So when you increase the du by dy, apparent viscosity increases. That means slope increases. And beta, whenever that apparent viscosity increases, that means such type of fluid is called the shear thickening fluid, right? Viscosity increases, apparent viscosity increases. That means such type of fluid is known as the shear thickening fluid. Shear thickening fluid. And beta, shear thickening fluid is also called dilatant fluid. Right? When you increase the du by dy and apparent viscosity increases, such type of fluid is known as the shear thickening fluid, because viscosity increases, so obviously your fluid becomes thick, right? So such kind of fluid is shear thickening fluid, or you can say dilatant fluid. So dilatant fluid is also called shear thickening fluid. Is it okay? Now, when n is less than 1, right? When n is less than 1, that means this n minus 1 is negative, na? N minus 1 is negative. Now, when n is less than 1 and when you increase du by dy, n is less than 1, and when you increase du by dy, what happened with the apparent viscosity? That apparent viscosity decreases. Because n is less than 1, so this term is less than 1. This term is negative. Now, if n is less than 1, so obviously this term is negative. So it is a divided by du by dy to the power something, a upon du by dy to the power something. And when you increase the du by dy, then obviously that apparent viscosity decreases, right? That means in such kind of situation, that viscosity decreases now, and viscosity or apparent viscosity decreases. So such type of fluid is called shear thinning fluid. And shear thinning fluid is also called pseudoplastic fluid. So I hope you can understand this. What is a dilatant fluid? In case of the dilatant fluid, when du by dy increases, that apparent viscosity increases. What is a pseudoplastic fluid? When you increase the du by dy or shear strain rate increases, in that case that apparent viscosity decreases. Is it clear? To everyone? Is it clear to everyone? So dilatant fluid, the first non-Newtonian fluid is dilatant fluid. That first non-Newtonian fluid is the dilatant fluid. So in case of the dilatant fluid, the tau naught is equal to 0. Correct now? The tau naught is equal to 0. And what about the n? That n is greater than 1. N is greater than 1. N is greater than 1. Right? You remember these things. These are the very, very important things. So in case of the dilatant fluid, the tau naught is equal to 0, n is greater than 1, and this type of fluid is also called, this type of fluid is also called shear thinning fluid. Shear thickening fluid. Such type of fluid is also called shear thickening fluid. And why it is called shear thickening fluid? Because as du by dy increases, that apparent viscosity increases. So if you plot shear stress versus shear strain rate plot for the dilatant fluid, right? This is the shear stress axis, this is the shear strain rate du by dy, right? So that graph, for the graph, that tau naught is 0. So tau naught is 0, so your graph starts from origin, from here, right? And as du by dy increases, the slope increases. That means apparent viscosity increases. So this is the graph for the dilatant fluid. This is the graph for the dilatant fluid. Is it clear? Okay, so can anyone tell me examples of dilatant fluid? Examples. So that butter, right? Butter is the example of dilatant fluid. Rice starch. This is also example of the dilatant fluid, right? Sugar solution. Sand solution in water. Etc. These are the example of the dilatant fluid. Right? So this is the first non-Newtonian fluid. Fine. Is it clear? Now come to the second non-Newtonian fluid. This is the first non-Newtonian fluid. Come to the second non-Newtonian fluid. Second non-Newtonian fluid is pseudoplastic. The second non-Newtonian fluid is pseudoplastic fluid. The second non-Newtonian fluid is pseudoplastic fluid. So what happened in case of the pseudoplastic fluid? What is the tau naught? The tau naught is 0. What is the n? N is less than 1. And we know that as du by dy increases, as shear strain rate increases, the deformation rate increases. So what happened with the apparent viscosity? That apparent viscosity decreases. Therefore such type of fluid is called shear thinning fluid. Right? So if you plot shear stress versus shear strain rate for the pseudoplastic fluid, shear stress versus shear strain rate, shear stress versus shear strain rate for the pseudoplastic fluid. So for the pseudoplastic fluid, tau naught is 0. So start from the origin. So this is the plot, right? So tau naught is 0. This graph is for the pseudoplastic fluid. Tau naught is 0 and n is less than 1. N is less than 1. Is it fine? Is it clear? Till this point it is clear? Tell me fast. Till this point it is clear? Okay. Now come to the examples. Come to the examples. 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 Right? Important examples. Na? These examples are very, very important. These examples are very, very important. That blood, milk, paint, right? Blood, milk, paint, polymer solution, polymer solutions, etc. These are the important examples, right? Blood, milk, paint, polymer solution. These are the example of the pseudoplastic fluid. Fine. Now, so if we compile dilatant, pseudoplastic and the Newtonian fluid, so we can compile in this way. We can compile in shear stress versus shear strain rate plot, right? So this is for Newtonian fluid, right? This is for Newtonian fluid, right? This is for Newtonian fluid, right? This is for Newtonian fluid. This is for Newtonian fluid. Tau naught is equal to 0, n is equal to 1, right? For dilatant fluid, this is the graph. I'm sorry, right? This is the graph for the dilatant fluid. That tau naught is equal to 0 and n is greater than 1, right? And this is the graph for the pseudoplastic fluid. This is the graph for the pseudoplastic fluid. This is graph for pseudoplastic fluid. Pseudoplastic fluid, right? And tau naught is equal to 0. Tau naught is equal to 0 and n is less than 1. Fine. Now come to the next, Bingham plastic. Come to the next, that is Bingham plastic. The third non-Newtonian fluid is a Bingham plastic. Bingham plastic. Bingham plastic fluid. So beta, if I am talking about the Bingham plastic fluid, so this is the fluid which requires minimum shear stress to establish the flow, right? Without giving a minimum amount of shear stress, it is not possible to flow. Such type of fluid is called the Bingham plastic fluid. And once the flow started, once you will provide the minimum amount of shear stress, then that fluid follows the Newtonian fluid. So Bingham plastic fluid is a fluid. It requires minimum it requires minimum shear stress. It requires minimum shear stress to start the flow. To start the flow. To start the flow. And once the flow started, once the flow started, once the flow started, once the flow started, then once the flow started, then tau versus shear stress versus shear strain rate graph is linear like a Newtonian fluid. Like Newtonian fluid. Like Newtonian fluid. Like Newtonian fluid. Right, now see, so if I plot shear stress versus shear strain rate, shear stress versus shear strain rate, so this is tau versus du by dy, right? So in this case, in the case of the Bingham plastic fluid, if you want to start the flow, the minimum amount of shear stress is required. Minimum amount of shear stress is required. So let us consider this is the minimum shear stress. This is the minimum shear stress, that is also called yield shear stress. That is also called yield shear stress. So this is the minimum shear stress. This is the minimum shear stress. Without providing this shear stress, it is not possible. It is not possible for this fluid to flow. So this is the, you can say this is the threshold shear stress. This is the minimum shear stress which is required to establish the flow or to start the flow. And once the flow started, then this is the shear stress versus shear strain rate plot. Right, so this graph is for the Bingham plastic fluid. This graph is for Bingham plastic. This graph is for Bingham plastic fluid. Bingham plastic fluid. This graph is for Bingham plastic fluid. Can anyone tell me examples? Can anyone tell me examples? Examples of Bingham plastic fluid. Can anyone tell me examples? Examples of Bingham plastic fluid. Examples. Your toothpaste. Toothpaste. Right? Your toothpaste is example of the Bingham plastic fluid. Shaving cream. That shaving cream. Shaving cream is example of the Bingham plastic fluid. The drilling mud. Right? Drilling mud. Drilling mud. Drilling mud. This is the example of the Bingham plastic fluid. Right? Mayonnaise. Right? Mayonnaise. Mayonnaise. Mayonnaise is the example of the Bingham plastic fluid. So these are the some important examples. Right? Especially the toothpaste is very, very important. Number of times it is asked. Right? Toothpaste is the example of the Bingham plastic fluid. So tell me, in this case, obviously in this case, in case of the Bingham plastic fluid, your tau naught is not equal to 0. Right? Tau naught is not equal to 0. Tau naught is not equal to 0. And n is equal to 1. N is equal to 1. Right? Tau naught for Bingham plastic fluid, tau naught is not equal to 0 and n is equal to 1. Right? So these are the time independent. These are the time independent non-Newtonian fluid. These are the time independent non-Newtonian fluid. Right? Now come to the time dependent non-Newtonian fluids. Come to the time dependent time dependent non-Newtonian fluids. Non-Newtonian time dependent non-Newtonian fluids. Time dependent. So I already told you time dependent non-Newtonian fluids are two types, right? One is the rheopactic fluid and second one is a thixotropic. Rheopactic. That first one is a rheopactic. Rheopactic fluid, right? And what happened in case of the rheopactic fluid? In case of the rheopactic fluid, as time increases, that apparent viscosity increases, right? Time increases in case of the rheopactic fluid as time increases. As time increases, this apparent viscosity increases. Time increases, that apparent viscosity increases. Therefore, it is called time thickening fluid, right? Time thickening fluid. Rheopactic fluids are also called time thickening fluid. Time thickening fluid, right? If I'm talking about the examples, right? If I'm talking about the examples. So the first example is gypsum in water, right? Gypsum in water, right? This is a one example. That another example is nail polish. Another example is nail polish. This is also example of the rheopactic fluid, right? So beta, these are the important examples which are asked in the examination, right? So example of rheopactic fluid is a gypsum in water and the nail polish. So now come to the second one is a thixotropic. Rheopactic. Now come to the second one. The second one is a thixotropic. Second one is a thixotropic fluid. So it is just opposite of rheopactic, right? So in case of the thixotropic fluid, as time increases, this apparent viscosity decreases. Time increases, apparent viscosity decreases. And this type of fluid is called shear thinning fluid. This type of fluid is called shear thinning, right? Shear thinning fluid. Right? And if I'm talking about the example, that printer ink. This is important example. Now, printer ink is an example of the thixotropic fluid. Is it fine? Okay. So if you draw plot between apparent viscosity versus time, if you plot graph between apparent viscosity versus time, correct na? Apparent viscosity versus time. So apparent viscosity versus time. So tell me beta, this is the graph for a line which is parallel to time axis. This is the graph for, tell me, This is the graph for, this graph shows your viscosity or apparent viscosity is not function of time. So this is the graph for Newtonian fluid. 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 Right? This is the graph for the Newtonian fluid. Now, tell me, this graph is for, right? As time increases, that apparent viscosity increases. This graph is for, this graph is for reviopactic fluid. This graph is for, this graph is for reviopactic fluid. This graph is for reviopactic fluid. Right? As time increases, apparent viscosity increases. So this graph is for the reviopactic fluid. And this graph is for, tell me, this is the graph for the thixotropic, obviously, right? Opposite to the reviopactic. So as time increases, apparent viscosity decreases. So this graph is for thixotropic fluid. This graph is for thixotropic fluid. Is it fine? Is it clear? Is it fine? Is it clear? Okay. Can anyone tell me? Can anyone tell me in tau versus du by dy plot, tau versus du by dy plot, graph for the ideal fluid? Can anyone tell me graph for ideal fluid? For ideal fluid. For ideal fluid. For ideal fluid. Can you show ideal fluid in this graph? Can you show ideal fluid in this graph? Can you show ideal fluid in this graph? In shear stress versus shear strain rate plot, can you show ideal fluid? Yes, we can show. We know that in case of the ideal fluid, that viscosity is 0. We know that in case of the ideal fluid, that viscosity is 0. And viscosity is 0, that means viscosity is 0, that means that du by dy is 0. Each layer having the same velocity. Du by dy is 0. Right? And also, right, du by dy is 0. Du by dy is 0. Sorry. I'm sorry. That mu is equal to 0. So tau is equal to each layer, or layer does not experiences the shear stress. Sorry. Right? When in case of the ideal fluid, that viscosity is 0 and viscosity is 0, that means layer does not experiences any shear stress. Layer does not experiences the any shear stress, right? So we can say, right, this is the graph for the ideal fluid. 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 Right? The shear stress is 0. Right? None of the layer experiences the shear stress. So this is the graph for the ideal fluid. Now if I'm talking about the ideal solid, for ideal solid, for ideal solid, so we know that in case of the ideal solid means there is no change in relative position of the particle under the influence of forces, moments. Such type of solid is known as the ideal solid. So we know that in case of the ideal solid, this du by dy is equal to 0. In case of the ideal solid, that du by dy is equal to 0. Right? So obviously, if this axis represent the ideal fluid, so obviously this axis represent the ideal solid. So this is the graph for the ideal solid. This is the graph for the ideal solid. This is the graph for ideal solid. Is it okay? Fine. So in case of the non-Newtonian fluid, you are getting 3 or 4 types of question basically, right? In our fluid mechanics subject, normally we are dealing with the Newtonian fluids. We are dealing with the Newtonian fluids, but sometime question come from the non-Newtonian fluids also. So in case of the non-Newtonian fluids, probably you are getting 3 or 4 type of question. The first question is related to the graph. First question is related to the graph. Second question is related with the tau naught and the n value, right? Second question is related with the tau naught and the n value. Third question is related with the examples, like in question it is asked that blood is an example of, right? Blood is an example of Newtonian fluid, thixotropic fluid, or pseudoplastic fluid, Bingham plastic fluid, like that, right? So third question you are getting from the examples, right? And fourth question is like that, right? Fourth question is like that. So in non-Newtonian fluids, you are getting 4 types of problem. The first type of problem is related with the graph, which graph is for which fluid. Second question is related with the value of tau naught and the n. Third question is related with the examples, and fourth question is related with this shear stress versus, right? This type of question basically, right? In this type of question, shear stress and the shear strain rate values are given, and in question it is asked, tell me which kind of fluid it is, like that. So this is the fourth category of problem. So in this question it is given that in an experiment, the following shear stress versus time rate of shear strain values are obtained for a fluid. How can the fluid be classified? A, Newtonian fluid; B, Bingham plastic fluid; C, pseudoplastic fluid; and D is a non-Newtonian fluid. So basically this is the you can say these are the values of the shear stress and the shear strain rate. So this row represent the shear stress value, and this row represent the shear strain rate, right? That means du by dy, right? Now we know the Wallah model, and as per the Wallah model, we know that tau is equal to tau naught plus a du by dy to the power n. We know that, where tau naught, a, and n are constant. Tau naught, a, and n are constant. Now can we find out the value of tau naught, a, and n by using the boundary conditions? Yes, we can find out. So we use first boundary condition. It is very much clear. At tau is equal to 0, the du by dy is 0, right? The first boundary condition, at tau is equal to 0, that du by dy is equal to 0, right? Or you can say at du by dy is 0, tau is 0. So if you use this boundary condition, then it is very much clear. Tau is equal to 0, du by dy is equal to 0. That means tau naught is equal to 0. Tau naught is equal to 0, right? Tau naught is equal to 0. So since tau naught is equal to 0, that means it is very much clear this fluid is not a Bingham plastic fluid, because in case of the Bingham plastic fluid, that tau naught is non-zero. Tau naught is not equal to 0, but here what we are getting tau naught is equal to 0. So obviously if you see this option, Bingham plastic fluid is not possible. Bingham plastic fluid is not possible, right? So this is one boundary condition. So from first boundary condition we can say tau naught is equal to 0, and since we know that tau naught is equal to 0, so we can say this fluid is it is not possible this fluid is a Bingham plastic fluid, because in case of the Bingham plastic fluid, tau naught is non-zero. Fine. Now come to the second boundary condition. Second boundary condition. Use second boundary condition at tau is equal to 2, at tau is equal to 1.4. I'm sorry. At tau is equal to 1.4, 1.4, that du by dy is at tau is equal to 1.4, du by dy is equal to 2. Correct, na? So 1.4 is equal to 1.4 is equal to tau naught is 0, a 2 to the power n. Right? You can say this is the equation number 1. You can say this is the equation number 1. Right? Now use another boundary condition. At tau is equal to 2.6. Tau is equal to 2.6. That du by dy is tau is equal to 2.6. That du by dy is equal to 3. Du by dy is equal to 3. And this is equal to 2.6 is equal to a multiplied by 3 to the power n. This is the equation number 2. This is equation number 2. Right? Now divide equation 2 and divide equation 2 to equation 1. Equation 2 divided by equation 1. Right? Equation 2. So this is 2.6 divided by 1.4 is equal to a 3 to the power n upon a 2 to the power n. Right? So from here you can easily calculate the value of n. So tell me, what is the value of n? What is the value of n? N is greater than 1 or less than 1? Tell me, what is the value of n? Tell me, what is the value of n? What is the value of n? Take log, na? Take both side log. Right? ln 2.6 to 1.4 is equal to n ln 3 by 2. Right? So what is the value of n? What is the value of n? Tell me, what is the value of n? Greater than 1 or less than 1? So this is ln 2.6, 1.4, ln 1.5. Sorry. So this value comes 1.526, which is greater than 1. Right? N value is greater than 1. So beta, tau naught is 0. Tau naught is 0. And n is greater than 1. So tell me which kind of fluid it is. Tell me which kind of fluid it is. Tell me which kind of fluid it is. So obviously it is dilatant fluid. It is dilatant fluid. It is dilatant fluid. It is dilatant fluid. Is it clear? So this fluid is a dilatant fluid. So correct answer is D. D is the correct one. Right? Correct answer is D. D is the correct one. Okay, fine. Is it clear to everyone? So I hope you understand each and everything related to the non-Newtonian fluid. I hope you can understand this. Okay. So this is all about today's session. Okay. And if you have any doubt, you can ask me. Join Telegram channel, na? Join Telegram channel, and if you have any doubt related to this or any topic, you can ask in the Telegram also. Okay, so thank you so much guys, and bye bye, take care, and good night everyone, good night.